Water filling power allocation algorithm for joint utility optimization in femtocell networks. Abstract. The ongoing evolution of personal mobile devices capabilities and wireless technologies result in a huge growth of traffic on mobile networks 3G and 4G. One of the most promising approaches to handle this data crisis is to offload the fast-growing traffic onto femtocell networks. Since both the 3G and 4G microcell and femtocell operate on the same license spectrum, the cross-tier interference should be well managed. In this paper, we propose a utility-based transmission power allocation policy for the uplink transmission in femtocell networks. Our main motivation is designed the transmission power allocation policy aiming at optimizing the joint utility of femtocell users FEU subject to interference temperature constraint at the microcell base station MBS side. We provide a novel floating ceiling water filling FCWF algorithm with a little computational overhead to obtaining the optimal solution for the joint utility optimization problem. Numerical results confirm that the joint utility and the average SINR can be significantly improved with the proposed methods. Introduction. With a wide gap between the existing network capacity and the traffic demand of users, mobile network operators MNO are struggling to cope with the rapid growing capacity requirement within heterogeneous network headnets. In particular, the witnesses of the massive growth of indoor traffic demand in recent years in the main driver behind the adoption of femtocell networks, which can be deployed indoors to provide high network capacity and improved coverage by reusing the licensed spectrum of the microcell. From MNO's viewpoint, femtocell are also cost-effective solutions. Due to the small size of femtocell base stations, FBS, they can be deployed in any enterprise or residential homes and utilize the existing wire networks for internet connections. Deploying femtocell therefore generated much lower capacity expenditure (CapEx) and then operating expenses (OpEx) than the microcell. The benefits the femtocell deployment have been well assessed in first. Currently, worldwide MNOs such as AT&T Mobile Telesystem, FNR, Sprint, Nextel, Verizon, James, etc. have launched the femtocell services since 2009. According to the market status report of SmartCell Forum 2, femtocell shipments have been reached 40 million, with 78 growths in the enterprise shipment from 2015 to 2016. It is also estimated that the femtocell revenue is going to $6 billion in 2020. With the emergence, femtocell mobile networks are now involved in a major transformation toward a distributed architecture from the conventional centralized on one tree. Namely, each femtocell has to make the decision on spectrum resources allocated and take charge of interference measurement individually. 4 and 5. Spectrum allocation strategy can be classified into two categories, such as macro femtocell headnets, spectrum sharing, and then spectrum splitting. In the spectrum sharing strategy, MNOs share the same frequency between the microcell and femtocells. Hence, cross-tier interference may cause poor system performance unless they are well managed. In the spectrum splitting strategy, spectrum is divided for exclusive usage in each microcell and femtocell, and cross-tier interference could therefore be avoided. In this paper, we restrict our attention to a spectrum sharing strategy. Our main motivation is to design the transmission power allocation policy aiming at optimizing the joint utility of femtocell users (FEUs). Subject to interference temperature constraint At the microcell base station (MBS) side, the transmission power allocation problem is resolved by convex optimization. The remainder of our article is organized as follows. Related work and our research interests are introduced in section 2. The proposed transmission power allocation policy and the water filling algorithm used to solve the joint utility algorithm problem are presented in section 3. Numerical results are provided in section 3. Section 4. Finally, this paper is concluded in section 5. Related work and main interest. Interference measurement in headnets have attracted intensive research effort over the last decade. One thread of research focused on designing transmission power allocation policy for alleviating cross-tier interference. In 6, the authors proposed a distributed power control scheme for macro femtoheadnet in order to alleviate interference between the macro cell and femtocells. In 7th, the author proposed an optimal cross-layer resources allocation policy aiming at maximizing the throughput for the FEU. The HFU. The optimization problem is modeled as non-cooperative games, the Nash equilibrium solution of which is obtained using distributed algorithm. In 8 and 9, the author studied the transmission power allocation in macro femto headnets with the emphasis on obtaining an incentive comparative solution in 10 and 11. The author focused on improving the power consumption efficiency in the design of spectrum resources sharing and then transmission power allocation algorithms. Since FEUs tend to behave selfishly without considering the interference introduced to macro cell, another thread of research focused on using pricing as an incentive mechanism for encouraging FEUs to cooperate with each other to mitigate interference. Several pricing schemes have been proposed for macro femto headnets. In 12, the authors propose an integrate pricing and the resources allocating framework aiming at optimizing the revenue of monopolistic wireless services provided in a two-tier macro femto network. In 13, the authors investigated MNO's revenue, user surplus, and then social welfare under flat rate and then usage-based pricing in two-tier macro femto network. The resources allocation and network revenue optimization problem has also been extensively studied. 14 and 15, where the author investigate the user incentives for the adoption of Femtocell on the top of the macro cell. Our work is inspired by the semi-work 16, where the authors studied the price-based transmission power allocation policy for the uplink transmission is sparsely deployed femtocells, assuming that the MBS protects itself by imposing cross-tier interference prices on the FEUs. Step Berlin game is then modeled to study the comparative interaction between the MBS and FEUs. The equilibrium of the Stackelberg game is obtained by solving both an utility optimization problem of FEUs revenue optimization problem of MBS. We argue that such interference prices are updated dynamically based on time-varying channel conditions, which may increase the user's uncertainty about their cost and burden of dynamic decision making. In this paper, instead of using price as a signal to control the received interference at the MBS, we assume that individual interference constraint can be directly imposed on FEUs. Our main motivation is designed to transmission power allocation policy aiming at optimizing the joint utility of FEUs subject to a total interference temperature constraint at the MBS side. We provide a novel floating ceiling water filling FCWF algorithm with the computational overhead to obtaining the optimal solution for the joint utility optimization problems. To our knowledge, this is the first work that addresses the joint utility optimization problem in macro femto headnets using filter filling algorithms. Transmission power allocation policy. We consider a macro femto headnets where a set of FBS are sparsely deployed inside the coverage of MBS. We focus on spectrum sharing mode where the same licensed spectrum is shared between the macrocell and femtocells. Each femtocell can serve the multiple FUs, and the different FU may have different QoS preferences. An inference temperature constraint is imposed each femtocell in order to mitigate constraint imposed on each femtocell in order to mitigate the over interference introduced to macro users MUs. Furthermore, we focus on uplink transmission analysis. For simplicity, we assume that FU's adoption of time division multiplexing access TDMA to transmit data, and for one femtocell, only one FU can attempt to transmit data in each time slot, just like 16. It is worth pointing out that a similar analysis for the multi-user scenario can be performed. As shown in Figure 1, the channel gained from FUI, FBSJ is denoted by HJI, and the channel power gain from FUI to the MBS is given by GI. The transmitting power level for FUI is denoted by PI. The received signal to interference plus noises relative SINR and FBSI for FUI can therefore be expressed as where an I denoted all FUs except FUI, P minus I denoted a set of transmission power allocation for all FUs except FUI, and then sigma scale is background noise level. A summary of the main notation used throughout the power paper is given in Table 1. We assume that femtocell that reuse the same spectrum should be located far away from each other, i.e., for example, sparse deployment scenario. This way, the co-tier interference could be negligible, namely Hij equals J, I, not J. The problem of solving transmission power allocation can therefore be simplified, and then closed form power allocation solutions can be obtained. At the FES side, the received SINR at the FBS for FUIs is denoted by Ri as follows: Ri equals sigma pi hi I n. Utility of FU is modeled as a logarithm function of received SINR, where lambda I is a user-dependent factor indicating the scale of its utility function, for example, utility gain. Our transmission power allocation problem is formulated to optimize the joint utility of the FUs under the interference constraint, where Q denotes the maximum level of interference that the MBS can tolerate. Proposition. The overall utility is maximized when the cross-tier aggregation interference and MBS reach the maximum level of interference. Sigma I equal 1 and PIG equal Q. Proof. Assume that n I equal first sigma and PIGI Q, then at least there is a FUJ that can increase its utility by increasing its power level by Gj Q minus without reducing the utility of other FUs. Through proof by contradiction, we can conclude that the overall utility is maximized when the interference at MDS reaches the maximum level of interference. By using the proposition first, problem P1 could be transformed to the following problems. max p lambda log first plus rho pi hi subject to proposition 2. The optimal solution pi n of problem p2 is unique where proof as shown in EQ5. EQ5 the object function is strictly concave and interesting function of pi. The constraints are affine. Therefore, P2 is a convex optimization problem, the optimal solution of which can be characterized by using the Karoshi-Tuka optimal conditions 18 and 19. The corresponding Lagrangian form of problem P2 is like this, where U, Ui, and V are Lagrangian multipliers. The KKT conditions are given as follows. Eliminating U, we have the stationary and complementary slackness in EQA implies that equation 10 can be rewritten as follows. With plus max transmission power allocation Pi, I and needs to be feasible, which gives the ground level of each tank is given by HIGI sigma square. We then increase the fluid level of V until the total amount of water reaches Q. The depth of watershed region in each tank is optimal value of GIPI. The ground level of each tank is given by HIGI sigma square. We then increase the fluid level of V until the total amount of water reaches Q. The depth of watershed region in each tank is the optimal value of GIPI. Illustration of the floating ceiling, water filling, WC/WF algorithms. We first consider that all FUs are being homogeneous, namely, they have the same utility gain. For example, lambda equation is transformed into the following equation. Equation 13 is a piecewise linear increases function of with breakpoint at HIGI sigma square. Therefore, there are unique solutions for equation 13. Water filling algorithm 18 is employed to obtaining the optimal solution. As shown in figure 2, HIGI sigma 2 is regarding as the ground level of tank I. We then increase the fluid level until the total amount of water reaches Q. The depth of water in tanks I is the optimal value of GIPI square. Then we consider that all FUs are being heterogeneous, namely the may have different utility gain. As shown in figure 2, the sealing height of tank I, for example, V square lambda I is then proportional to the QoS preference, lambda I floating ceiling. Similarly, we increase the fluid level until the total amount of water reaches the depth of the water in tanks I, then the optimal value of GIPI. The Lagrangian multiplier V has several interpretations. We may view V as the implied cost of unit interference on MBS. Alternatively, V is the shadow prices of additional interference at MBS. According to the conclusion shown in 16, the revenue at the MBS side could be maximized when appropriate shadow prices are imposed on FUs. Algorithm 1 summarizes the steps involved in finding optimal transmission power allocation strategies at each FBS. The computational complexity order N Q max. Note that larger larger lambda V can reduce the computational complexity, but cause a gap between the actual interference, introduce the maximum level of interference allowed, for example, Q. Numerical analysis. In the section, the extensive simulations implemented in MATLAB are 2016 are concluded validate efficiently of the proposed transmission power allocation policy. We consider a macro femto handnet and 3 FBS and deployed in the coverage and FBS. Without loss of generality, we assume that channel of gains from FU's FBS are given as follows: H1, 1, H2, 2, H3, 3 equal 1. The channel gains from FUs to the MBS, for example G1, G2, and G3 are uniformly distributed in the interval 0,1. Furthermore, the utility gain, for example lambda 1, lambda 2, and lambda 3 are randomly chosen from the interval 0,1. For our comparison purpose, we introduced even interference, even power, and price-based 16 schemes as follows. Even interference, the total interference constraint Q is evenly divided and imposed on each FUs. Comparison between proposed method and existing method. Even power. Transmission powers allocated for different FUs are identical. The transmission power is leveraged until the overall interference at MBS equal to Q. Price-based optimal transmission power and prices for different FUs are set according to EQ and then equation 15 and equation 24 shown in 16. Observation as shown in figure 3 for both the joint utility of FUs and the average SINR increases with the increasing of interference power constraint, comparing with the even power, even interference, and then price-based method. The joint utility of the proposed method is increased by 15.8%, 5.7%, and 3.0%. The average SINR of the proposed method is increased by 238.3%, 10.1%, and then 86.5% respectively. For a better comparison, we then assume that utility gain are all equal to 1. Then channel gains are given as follows: H11, H22 equal 1, H33 equal 1, G1 equal G3, 03, G2 equal 06, and then G3 equal 0.9. Observation 2. As shown in figure 4, the shown price imposed on FUs decreases with the increasing of the power interference constraint Q. Observation 3. As shown in figure 5, both transmission power allocation and the individual utility increases with the increasing of the power interference constraint Q. Comparing among FUs, the one with the normal channel gain MBS could obtain higher power allocation under the proposed method and then achieves higher individual utility correspondingly. This is not surprising because in order to maximize the joint utility, we give higher priority to those FUs with better channel conditions. Furthermore, we fix the channel gains for all FUs to 1. For example, H1, H2, H3, G1, G2, G3 equal 1, and vary the utility gains as follows: lambda 1 equals 0.3, lambda 2 equals 0.6, and lambda 3 equals 0.9. As shown in figure 6, comparing among FUs. In order to maximize the joint utility, the one with higher utility gains could obtain higher power allocation under the proposed method and achieves higher individual utility correspondingly. Namely, under the proposed method, we also give higher priority to those FUs with higher utility gains in order to maximize the joint utility. Conclusion and future work. In this paper, we propose a water-filling transmission power allocation algorithm for joint utility algorithm in micro femtohelnets. The joint utility optimization problem with interference temperature constraint at the MBS side is resolved by convex optimization. Numerical results confirm that joint utility can be significantly improved with the proposed method. As future work, we intended to apply our power allocation policy to sparsely deployed femtocells where the Coulter interference could not be ignored, and investigate the fairness issues of transmission power allocation in micro femtohelnets.